Okay, in this video we're going to start talking about electric fields, and they're kind of a difficult concept to wrap your head around because they're not something that you can see. Here's the idea, or why I came about it. You don't have to draw this. This is just something I want you to see with me. So let's say I have a charge here of plus Q, and another charge here of plus Q. We know that this one is going to feel a force. It's going to repel from that positive Q. But the people who were studying this thought that was kind of strange because if I want to put a force on something, I have to touch it, I have to push it or pull it. I can't do it from across the room. Okay? How can this charge put a force on this charge over here without ever touching it? How does this charge even know that this charge exists? So they came up with this idea that this first charge here is creating an electric field everywhere in space around it, okay, including at this point. And then this charge reacts to that electric field. So it really doesn't know that this charge exists. What it is reacting to is the electric field near it created by this charge. So what's happening is that charges react, okay, and by that we mean fields feel a force due to electric fields, and those electric fields are created by other charges. And the equation for it is going to be F equals E times Q. And then, by definition, the direction of the electric field equals the direction of the force on a positive charge. So what that means is, and you can draw this, if I have an electric field pointing this way, that's my electric field. If I put a positive in there, it's going to feel a force going in the same direction. But if I put a negative in there, it's going to feel a force going in the opposite direction. So we have an example here. I'm going to call this part A here, and then we're going to have part B here. A is going to be with the alpha particle, B is with an electron. So in part A, what is the magnitude and direction of the force on an alpha particle and an electric field of 200 newtons per coulomb west? So part A, we are going to say that we have an alpha. We have to remember that that is He24, which is 2 protons plus 2 neutrons. Then that means our charge is 2e, because you get 1 e for each proton. I'm going to convert that to coulombs. 1 e is equal to 1.6 times 10 to the minus 19 coulombs. I'm going to multiply across the top, and I get 3.2 times 10 to the minus 19 coulombs for my charge. And then I'm just going to use this new equation, F equals EQ. Now, I'm going to keep my units and my directions. I don't always do this, but I want you to see what happens if I do. I get 200 newtons per coulomb west times my charge is 3.2 times 10 to the minus 19 coulombs, and I end up with a force of 6.4 times 10 to the minus 17 newtons, because the coulombs cancel, and then my direction is going to be west. Okay, then in part B, we want to find it for an electron. Charge of an electron is minus 1e, so that's minus 1.6 times 10 to the minus 19 coulombs. Then using the same equation, the force on that is going to be 200 newtons per coulomb west times minus 1.6 times 10 to the minus 19 coulombs. And that's going to give me 3.2 times 10 to the minus 17. It's going to be negative because I'm multiplying a positive times a negative. Newtons west. Well, now if I look at that, I have a negative force west. That's really force eastward. So the force is equal to 3.2 times 10 to the minus 17 newtons east. Now I normally don't bother keeping the signs all the way through. I wouldn't have put this negative here. I just would have realized that since an electron's a negative charge, it's going to go the opposite way of the electric field, so it's going to end up going east. So let's sketch what's happening here. Here is our electric field pointing west. Here's our alpha particle. It's positive, so it's going to go west. And here's our electron. It's negative, so it's going to go the opposite way. Drawing electric fields. So we're going to start out with a little positive charge. All right. So these are going to be the electric fields created by the charge. So this isn't how they're going to react. This is the charge that's creating the electric field, and other charge are going to react to it. And remember, it's which way a positive would move. So we're going to use a positive, what they call test charge. So you imagine that in space around this, there's going to be a little positive charge. So let's put a little positive charge there. Now, which way is that little positive charge going to go? Well, it's going to go away from it, so it's going to go out this way. If I have a little positive charge there, it's going to go away from it. They don't have to draw the positive test charge. Just imagine, right there, there's a little positive test charge. It's going to go away. A little positive charge is going to go away. Away. So around a positive charge, the electric field always points away. So we'll make a note of that. E fields point away from positives. So again, this isn't how charges are reacting. These are the electric fields created by the charge. Then if I put a positive charge right here, it's going to go the same direction, so it's going to go this way. If I put a negative charge, it's going to go the opposite way. Now, if I have a negative charge, I imagine my little positive test charge right here. Which way is it going to go? It's going to see that negative charge. Since it's positive, it's going to be attracted to it, so it's going to want to go that way. So it's going to look like this. They point toward negative charges. If you memorize the electric fields point away from positives and towards negatives, it's going to make life a little bit easier. If I have a positive and a negative, okay, I start here. I imagine a little positive charge there, okay? It's going to be repelled from the positive in a lot more than it is attracted to the negative right now because it's closer to the positive. So it starts out just trying to get away from that positive, but then it sees that negative there, and it'll curl down to it. And the same thing down here. It's going to be repelled from the positive and then end up curling into the negative. And you end up with something that looks like this. So that would be electric charge for that combination. If I had a positive and a positive, I imagine a little positive charge there. At first, it's going to repel from this positive it's near to, but as it gets closer to that other positive, it's going to curl away from that one as well, because it's repelled from it. And it's symmetrical, so one down here is going to repel down like this. One over here is going to start out trying to get away from that one, and then curl away from the one on the left, like this. And you end up with an electric field that looks like that. And the last one we're going to do is a special case. It's parallel plates. So I have two metal plates. Say one is positive, one is negative. What's going to happen is if I put a positive in here, it's going to repel from the positives and be attracted to the negatives. Like this. Now, the reason this is important is this. The field is strongest where the lines are close together. Let's look at that first one that we did. Right? The electric field is going to be stronger when I'm nearer to the positive charge. It gets weaker as I go out. And I can tell that because when I'm near it, right here, the electric fields aren't really close together. And as I get farther away, the electric field lines get farther apart. So it's getting weaker and weaker. If I look at this, the field lines are parallel. They're not getting closer and farther apart, so the field is constant. And that's something you want to know. For parallel plates, the electric field is going to be constant. Now, for the system charged below, stretch the electric field due to each charge and the net electric field for points A, B, and C. So let's take a look at point A. Remember, we imagine a positive charge there. So I put my pen at A and I imagine that that pen is a positive charge. Which way is it going to go because of this positive charge over here? Well, it's going to try to get away from it, so it's going to go this way. And I could label that E because of the +3 charge. So the electric field because of that one is going to be that way. Okay? Now, how about because of the negative charge? Okay, so if I imagine a positive charge there, it's going to go towards the negative charge. It's going to point the same direction. So this is going to be E due to the Q. They're both pointing in the same direction, so to find the net, I would add them together. All right? How about, now another way to look at it is this. Electric fields point away from positives, so if I'm at A, I'm going to point away from this positive over here. They point toward negative, so if I'm at A, it's going to point toward this one. So they're both pointing left. Okay? Now, at point B, this one right here, the +3, I point away from positive. So I imagine at point B, and I point away from the positive. So that's going to be E due to the 3. Now, if I'm at B, and I look at the negative over here, I'm going to go toward the negative. The electric field is pointing towards negative. So E for the Q is going to be that way. Now you notice something. I drew the electric field for Q shorter than the one for the 3. There's 2 reasons for it. A charge of 3 is bigger than a charge of 1, so that's going to give you a bigger electric field. And it's also closer, so I know E3 is going to be greater than the E due to the Q charge. And then my E net then is going to be that way because the one going to the right is bigger than the one going to the left. The last one is for point C here. So I imagine myself at point C, and I have to go away from this plus charge. So I'm going to go this way, away from it. That's going to be my E3. I imagine myself at C, I'm going to have to go towards the Q. So along this direction, I'm going to go towards it. So that'd be E for the Q. Again, notice I've made the 3 bigger than I made the 1 for the Q because it's a bigger charge. Now, which way is it going to go altogether? Well, it's going to go someplace in between the 2. We have to go back to like adding vectors. So if you remember for adding vectors, you have to draw them tip to tail. So I can slide this EQ up here maybe. And then my E net would be off this way. Now we're not going to do any math with that right now, but that's what's coming. Now to calculate the electric field caused by a point charge, we use this equation. E equals KQ over R squared. It looks like, you don't have to write this, but it looks like this equation, just missing a Q. So that's one way to remember it. Now, what is the magnitude and direction of electric field at distance 2 meters from a charge of -3 MC? We got to figure out what that stands for. So I'm going to draw a little picture. I have this charge here. Q is -3. Now, M stands for milli. It's on the front of the reference table, and that means times 10 to the -3rd. So we're going to write times 10 -3rd coulombs. Now, I don't find the electric field at that point. I find the electric field that it causes in space around it. And this says the distance of 2 meters away. So let's draw this point right here. We're going to say this is 2 meters. Okay, and I want to know what the electric field at that point is. Okay, so let's do the magnitude first. It says magnitude and direction. So magnitude is just how big it is. So we're going to use this new equation, KQ over R squared. It's 9 times 10 to the 9 times 3 times 10 to the minus third. I'm going to ignore the negative sign when I'm just trying to find the size of it. And then divide it by 2 squared. And that's going to give me 6.75 times 10 to the 6th, the units per order of newtons per coulomb. So that's the magnitude. Now we have to figure out the direction. So I go back to my point. Remember, I'm finding the electric field at this point, not at the charge. And which way do electric fields point? Do they point towards negatives or away from negatives? They point towards negatives, so it's going to be this way. So we could say toward the negative 3 MC. So that was quite a bit. So we have to remember, how do charges react to electric fields? If there's an electric field there, and I put a charge in that electric field, it's going to feel a force. If it's positive, it goes the same way as the electric field. If it's negative, it goes the other way. So that's one thing. The other thing is, if I have a charge, and I don't know the electric field it creates around it, okay? The electric field is created by a charge. If the charge is positive, it points away from it. If it's negative, it points towards it.